let's talk a little bit more about rational numbers. So we've got our family of real numbers, and they can be broken down into rational numbers. They're all the ones that we can write as fractions. So terminating decimals, recurring decimals, and so on. And that, of course, gives us the other matching set, irrational numbers, and the definition simply is the ones that can't be written, so they're the ones that are not rational. Hence the prefix IR, which probably goes back to Latin. Anyone doing Latin? Probably has something to do with it, I'm sure, that's where it comes from. But all irrational numbers can be expressed as a unique, infinite decimal. So it's unique. No other number has the same value. Pi is probably the most famous of them all. Just going to do a little proof here. We're actually going to prove that the square root of 2 is in fact irrational, that we don't know what it is exactly. It's using a method known as proof by contradiction. Proof by contradiction. So what we do with proof by contradiction is we actually assume what it is that we don't want. I want to prove root 2 is irrational, so I'm actually going to assume the opposite. So let us assume the square root of 2 is indeed a rational number. Now, if that is true, I can write it as a fraction. So therefore, it can be written as a over b, where a are integers, and they have no common factor. Because if they had a common factor, I could simplify the fraction down. So a over b is in its simplest form. So no common factors. Alright, just playing around with that then, I get b root 2 is equal to a. If I square both sides, I get 2b squared is equal to a squared. Well, that's now telling me, because remember these were integers, no common factor, so the factors of a squared are 2 and b squared. So a squared must be divisible by 2. We know that. A squared must be an even number. But I also know this, any square that is divisible by 2 must be divisible by 4. Because if you're writing a square number down as a product of its prime factors, every factor must appear twice, because it's a square. And then go to the simplest one, 25, you get 5 times 5. 100 would be 10 times 10, but then each of those 10s would be 5 times 2. So you get 5 times 2 times 5 times 2. So every factor would be there twice. So what I'm saying here is, well, I know a squared is a square. If it's divisible by 2, it must be divisible by 4. So I know that. Well, if a squared is divisible by 4, remember we said a squared was the same as 2b squared. So 2b squared must equal 4k, where k is some integer. Now if that's true, b squared is equal to 2k. Okay? Dividing both sides by 2. So therefore, a squared and b squared are both divisible by 2 and have a common factor. But hang on, we just said a and b have no common factors. So therefore, a squared, because remember, all a squared's factors are simply the factors of a repeated. B squared's factors are the factors of b repeated. So if a squared and b squared have a common factor, a and b must have a common factor. But we said a and b don't have a common factor. There's the contradiction. We know a and b don't have a common factor. So therefore, if I've now contradicted myself, my original assumption must have been wrong. So if the square root of 2 is not rational, it must be irrational. Thus proving the square root of 2 is irrational. So that's a proof by contradiction. Couple of questions there to play with. Number 4 is doing a similar thing, proving the square root of 3. Same sort of idea. See how we go.